Hello, fancy folks. Welcome back to LuxeSci, a podcast to reignite your wonder by exploring the intersection of science and luxury. I'm your host, Dr. Lex, a former parasitologist turned consultant with over a decade of research experience and a fairly large shoe collection. In this episode, we're going to focus on a fashion item that was all over the runways this year. I'm talking bows and ribbons. From Miu Miu, Simone Rocha, and Sandy Liang all featured bows in a big way in their latest runway looks. Whether it was glued to the underside of their eyes, adorning Miu Miu's satin ballet flats, or turned into bags by Sandy Liang, there have been articles waxing poetic about the return of the ribbon and what it means in a time when being a woman seems to be under attack. But here at LuxeSci, we're asking a different question. First, where did they come from? And most importantly, are there ribbons in science? Can a seemingly feminine icon be advantageous in science? So if you've ever wondered what bows and ribbons have to do with protein folding and nerve endings, because honestly, who hasn't wondered that? Come along and explore with us and maybe learn a thing or two. I know I did. And if you like our content, please go ahead and use your perfectly manicured nails to hit that subscribe button. Help us spread the luxuriously scientific word. Now, the history of the ribbon is a little hard to pin down. As with lots of the topics we discuss here, its beginnings are a bit nebulous. But first, let's start with, what is a ribbon? Ribbons are narrow, woven strips or bands which are finished off on all edges. As with most things related to fabric, people have been weaving narrow strips of fabric since around the Neolithic period. Evidence of woven bands were found in Turkey dating from around 6000 BCE. It was customary for ancient Greeks, Egyptians, Sumerians, and Aztecs to wear ribbons as hair adornments. Ribbons as we know them came into being in the Middle Ages when new loom technology allowed for more complex woven textiles. As early as the 11th century, lighter weight ribbons were being made in Saint-Étienne, France. These were probably more functional than decorative. Starting in the 14th century, ribbons became more decorative and more popular, with some countries making laws that only the nobility could wear ribbons. It was quite common then to have laws governing who could wear what based on social status. The popularity of ribbons continued well into Victorian times, with male usage of ribbons declining by the 17th century. This was due to the decline in a popular hairstyle for men called the lovelock hairstyle, a long plait draped over the chest and tied with a ribbon at the end. At the same time, female usage picked up as more elaborate hairstyles and clothing were becoming in vogue. Interestingly, the connection of bows and romance flourished again in the 1900s with an article of Life magazine detailing how the position of a girl's bow in her hair communicated whether she was taken, single, or generally not interested. I kind of wish that still existed, to be honest. While there's definitely physics and mathematics associated with ribbons and how they bend and twist, that is not what we are going to be discussing, mostly because physics isn't my favorite scientific area, but also because there is some fascinating science around how ribbons show up in the natural world and how scientists are harnessing the advantages of ribbons to advance science. So let's start with some basics. Proteins. We've discussed proteins lots of times before on the show. The most straightforward way to think about protein production is DNA becoming RNA, becoming amino acids that make proteins. And proteins are the action powerhouse of the biological world. You can see that in their name, coming from the Greek word proteos, meaning primary. They are the building blocks of biological tissue, skin, hair, nails, etc., and also act as enzymes, antibodies, and all sorts of things that drive life as we know it. They are made up of amino acids. Amino acids are small building blocks of proteins. There are 20 to 22 types, and all these different combinations are made into proteins. And you've probably heard of some of them potentially as dietary supplements like glutamine. What amino acids make up a protein determine how that protein folds, i.e. its 3D structure. Protein folding is relatively conserved, with similar amino acid content equaling similar folding. This is important because if a scientist can determine the fold or shape of a protein, this will give clues as to the function of a protein. Now let's get down to some basics about protein folding. So everybody strap in, we're going on a mini biochem lesson here. There are 4 levels of folding proteins. The first is primary, and this is the protein sequence, the line of amino acids that make up a protein. This is the first thing that determines a protein's shape. The secondary is the first layer of folding that involves the backbone of a protein and not the side chains. So the side chains are chemical groups that stick out from that line of amino acids. And the common secondary foldings are alpha helices, beta sheets, and turns, which maybe sounds a little bit like a ribbon already. The tertiary folding is a 3D arrangement of all the atoms in the protein. Or, if you want to be super sciencey, it's the precise spatial coordination of the secondary structure elements and the location of all of the functional groups. And tertiary folding can be folds or motifs or domains, and those are just different ways that scientists classify tertiary folding. Quaternary folding is the structure of many proteins or a mass of proteins, and it's a spatial arrangement of all the subunits within that mass. So what about the ribbons? They appear in two prominent places, and the first is actually not in the protein, but the way that we look at proteins. The ribbon diagram to show protein structure was developed by Jane Richardson in the 1980s as a better way to show the structures of proteins and to replace the wire models that were used at the time. For a review article, Jane had to draw a bunch of protein structures, and she started out drawing smooth ribbons over the atoms of a computer graphic printout. And this wasn't quite right, so she consulted her mother-in-law, who was an artist, and Irving Geis, who was a Scientific American illustrator. And she still didn't quite get it how she wanted it. So she took a belt, and she studied what her eye saw when the belt was twisted, and she tried to draw that. And it was published in 1981 for the first time. This ribbon diagram takes the primary structure and shows the twist and fold like a piece of ribbon. And these are the alpha helices turn into coils, and beta sheets are long, flat arrows. It lets you see the common and related structures much more easily. And this was a really revolutionary way to depict protein structures, and one that is still being used today. However, it shouldn't be used alone because some of the information about the protein, such as the side chains of the amino acids, gets lost in this representation of protein structure. But there are also more defined ribbon-like structures in proteins. Many of these are in DNA binding proteins, which are proteins that bind to DNA. Every once in a while, scientists name things really obviously. And these DNA binding proteins are generally involved in DNA replication or transcription, which is reading the DNA to turn it into RNA, to turn it into amino acids. One motif that is very familiar and very common in this family of proteins is called a beta ribbon motif. And this is two beta strands that look like a hairpin, like an old-fashioned hairpin like your grandma might have used. And these two beta strands wrap around the DNA, and it's called a beta ribbon because it looks like a piece of ribbon that's been folded in half. And this beta ribbon motif is found in a lot of prokaryotic organisms like bacteria. Okay, I haven't talked that much about protein structure since my biochem class in undergrad. So to summarize, protein structure is important to protein function. Protein structure can look like ribbons, and some structures are classified as ribbons, especially those proteins involved in DNA binding. A useful visualization of protein structure is a ribbon diagram where the primary structure of the protein is represented as a ribbon. So that's ribbon science on a very microscopic level. What if we zoom out a little bit? Did you know that you need ribbons to sense things? Synaptic ribbons are organelles, organized and specialized structures in a cell, that are located in sensory neurons in the visual, auditory, and equilibrium system. These ribbons act like a conveyor belt in response to stimuli. They move vesicles, little containers containing neurotransmitters, to the area to be released to send the signal along. So a signal travels along neurons by these neurotransmitters that go across the synapses, the gaps in between the neurons. So that's how the signal gets propagated or sent along your nervous system. So in your visual and auditory and equilibrium systems, this is being done pretty much continuously because of the constant need to send these signals along this chain. So think about the rods and cones in your eyes. Your eyes are constantly acquiring information that must be processed, and thus the signals along these neurons are constant as well. So recent evidence shows that it might not be sustained release of neurotransmitters, but transient and synchronous release of neurotransmitters from these synaptic ribbons that allows you to input and process visual and auditory information. This would imply that these synaptic ribbons have greater control over the vesicles, over the neurotransmitters, than previously thought. All I can say is that the little I keep learning about anything to do with neuroscience, the more impressed I am. It is a beautifully complex and coordinated system. So we've gone from very microscopic protein structure to slightly more macroscopic neuron synapses, and now to something that's actually macroscopic that you can see with the naked eye, a worm. You all know I love my worms, so much so that I spent the better part of a decade learning about them and studying them. So now we're going to take a look at the ribbon worm, and they're from the phylum Nermertians, and these are ribbon worms, and they have around 1,300 species in this phylum. Most of the species are found in marine environments, and this phylum contains the Linnaeus longissimus, which is the longest animal on Earth, reaching lengths of 50 meters, or around 164 feet. Many species are brightly colored, and that's because they can be toxic. They have a proboscis, like a mosquito, and the toxins are thought to be located in the anterior or rear part of that proboscis. The marine species like to eat mollusks, crustaceans, and other worms. And some examples of their toxins are pyridine alkaloids, and these are nitrogen-containing compounds usually found in plants. One toxin in this family is nicotine, and these may cause paralysis in the crustaceans. And another toxin that they possess are tetrodotoxin, TTX, and that's the same toxin as a pufferfish, and that has a very strong paralytic effect. I, for one, am always excited to learn about a new kind of worm, though I think I'll be avoiding these ones if possible. While they're likely not toxic to humans, I can't imagine it would feel good to come in contact with one. Okay, so I know this has been a really heavy science episode, but I have one more super cool thing I'd like to share with you if you can hang in there with me. By the way, this is still way less painful than a full organic chemistry lecture, so you're welcome. I couldn't let this episode end without mentioning solar cells. For those of you who don't know, our audio engineer and sometimes co-host, Dr. Dimos, used to have a solar inverter company. He designed and manufactured devices that link solar panels to the power grid and to backup batteries. He's so smart. So we've talked a lot about solar power in our family, and we are generally green tech enthusiasts. When we were first dating, Dimos made me a bracelet that had a small solar cell on it and a purple LED light. When I went outside, the light lit up. It was very cool, but not very comfortable because it was made on a hair elastic, which, as we know, if you put on your wrist, kind of digs into your wrist a little bit. Sorry, Dimos. The field of wearable solar cells has been advancing, though. This is due to the rise in wearable technology. That technology, like your Apple Watch, needs a power source. While most of the power sources currently are batteries that are charged by plugging them in, imagine how cool it would be to use solar power one day. A group out of the University of Central Florida has been working on a flexible and low-cost photovoltaic solar cell device that is on a copper ribbon that can be woven into fabric and used for charging wearable devices. It integrates the solar cell with a supercapacitor, i.e. something that can hold energy really well, so it can work as an energy harvester and an energy storage device. Now, I'm not going to attempt the details here, since this is definitely not my field of expertise. And despite being married to an electrical engineer for almost 10 years now, I do not understand the ins and outs. I do think it would be very cool to have a solar charging wearable fabric, especially one that can store energy, kind of like a solar charged watch. Wow, what an episode. As usual, I did not expect to find so much cool science related to ribbons. I hope you hung in there with me and learned a little something about protein folding, marine worms, or solar charging fabric. For our glossary, we have proteins, which are the building blocks of biological tissues, organelles, which are organized and specialized structures in a cell, and supercapacitors, which are a type of electrochemical energy storage device that can store a lot. And now for some fun facts, just in case there's a lull in conversation. Did you know there are ribbons in your nervous system that help high traffic signaling involved in seeing and hearing? And also that one of the longest animals is a worm that measures up to 50 meters or 164 feet. And we may soon have ribbons that contain solar cells and can power wearable technology. Thank you so much for joining me on this episode of LuxeSci. LuxeSci is a production of Erevna Media, produced by me, Dr. Lex. Audio engineering by Dr. Dimos. Our theme music is Harlequin Mood by Burdy. We're all over social media at LuxeSci Pod. Please drop us a line and say hi. We love to hear from you. And don't forget to share us with a friend. We'd love to reach more people who would enjoy hearing about some luxurious science. Until next time.
Hey there, podcast listeners. Are you looking for a fresh podcast that dives into the realms of scientific wonders, shares unique career advice, and where you can learn about the stories of guests who made real scientific discoveries possible?
Then join us at Keep It Science as we aim to unravel mysteries, spark inspiration, and much more. We're all about bringing science closer to you.
We are your co-hosts, Dr. Elizabeth Kugler and
Dr. Nick Gaunt. So keep questioning, keep exploring, and most importantly, keep it science. Make sure to follow us on YouTube, LinkedIn, and X, or wherever you're listening to this from.
bye!